In this video, we're going to learn how to count the microscopic states of a system, also known as microstates, and we'll try to determine and look at a relationship between the number of microstates and spontaneity. I've heard many times that people erroneously refer to entropy as disorder or randomness. That couldn't be farther from the truth. In this video, we'll start to see what entropy truly is, which is a measure of how many possible arrangements a system can have. So if we look at our model over here of a lattice gas, and it's called the lattice gas because here we have our lattice, and inside of it we have our gas particles. And if we were to constrain this gas to this one location in the lattice, so now we have a pressurized gas over on the left-hand side, and we forbid it to fill the rest of the lattice, there's only one possible arrangement of these three indistinguishable gas particles. But anyone who's ever been around a compressed gas knows that a compressed gas will spontaneously expand if given the opportunity. So we know that spontaneity involves expansion of gases. We also know that spontaneity involves mixing. So if we have a solution and it's unmixed, solutions will tend to mix. Again, thermal equilibrium. So temperatures, if I have two objects that are touching each other and are at different temperatures, these temperatures will eventually come to thermal equilibrium. We know that all of these things happen, quote unquote, spontaneously. The question is, why do they happen spontaneously? And for that, we're going to have to develop a formalism for discussing these types of problems. So just one last example before we get into the counting. Here we have a pressure, a gas with inside of a container with a movable barrier or a piston. If we look over here and we calculate the pressure here on the right, we see that the pressure here on the right is 6 in 8. What those 8 units are, what the actual volume is, doesn't really matter, but there are 6 particles in 8 possible spaces. The pressure here on the left is only 2 in 8, and since we know that the pressure on the right is greater than the pressure on the left, the piston will move. When will it move? It'll move until the pressures on either side are equal. So you can calculate over here that we have the pressure on the left is equal to the pressure on the right. We know that this is a spontaneous change. What makes it spontaneous? Well, hopefully we'll see soon that if we were to calculate the total number of ways, which we'll call W, for the system on the left, and we were to calculate the total number of ways for this system at the end, the ways final will be greater than the ways initial. And when the number of ways the universe has to arrange itself increases, we call that a spontaneous change. So we'll see how to count those starting right now. So I would like you all to pause this video for a second and figure out the total arrangements that you could possibly have for 3 objects, A, B, and C. And assume that you are able to distinguish between all 3 objects. So pause the video and make your arrangements. Hopefully you've come up with these following arrangements. Your order need not necessarily be the same order that I have, but these are the total of 6 arrangements that I found for A, B, and C. Now what would happen if instead of all 3 of these being distinguishable, A and B were indistinguishable? Let's say A and B were actually not A and B at all, but rather were both A. So what would these arrangements look like? Again, you can pause the video now, come up with those arrangements, and then hit play. Hopefully you saw that your arrangements were AAC, ACA, AAC, ACA, CAA, CAA. Notice, however, here's ACA and ACA. Here's AAC and AAC, and here's CAA. We have 1, 2, 3 ways of arranging these three. Now these are three unique, each with 2 degeneracies. So it seems like 6 total arrangements is equal to the number of unique arrangements times the number of degeneracies. Let's see if this works if we keep going to a little bit of a larger system. So again, I'd like you to pause the video, and while you're there, enumerate all the possible arrangements for 4 objects, A, B, C, and D. Once you're done with that, you can hit unpause. So once you've had all of your arrangements, hopefully you found 24 arrangements of A, B, C, and D. Now I'd like you to assume that B and A are indistinguishable and C and D are indistinguishable, and turn all of your B's into A's and turn all of your D's into C's. And when you're done with that, you can hit play again. So we started with 24 arrangements of A, B, C, and D, and hopefully you've now figured out that there are only 6 unique ways of arranging them if there are twofold degeneracies of A and B and C and D. So, for example, notice A, B, C, D, B, A, C, D, BADC, ABDC, all 4 of these, even though they look very different, all start looking like AACC. So we have one unique arrangement with 4 degeneracies. So 6 unique arrangements, 4 total degeneracies, and that is equal to our 24 total arrangements. So those of you that have taken a little bit of statistics might recognize this. This 24 total is actually the 4 objects A, B, C, and D factorial. And the 4 degeneracies are actually just the 2 factorial degeneracies for A and B being the same, and 2 factorial degeneracies for C and D being the same. And if we do this, we get that 24 total divided by 2 factorial times 2 factorial, 4, and that's equal to the number of unique arrangements. And this number of unique arrangements, that's what we're going to call the number of ways. So the number of ways is going to be the number of unique arrangements, which is the total number of objects. In this case, we have 4 objects, but we'll call it, let's say, 4 objects factorial divided by the degeneracies 2 factorial, 2 factorial. So if we were to write a generic expression for the number of ways for arranging particles, j objects of one kind and k objects of another kind, we would write j plus k. That's the total number of objects, factorial. But since there are j degeneracies of one and k degeneracies of the other, we would divide by the degeneracies j factorial times k factorial. So let's see if we can try this out and do a nice simple calculation. How many unique or distinguishable ways would there be to distribute 2 solute particles and 4 solvent particles? I'd like to visualize that perhaps like this. So we can make the solvent particles O's on my lattice, and we can make my solute X. And I'd like to know how many unique ways there are for arranging this lattice. So hit pause and work on that, and when you're done, you can hit play. Well, there's a total of 4 plus 2 objects. 4 solvent, 2 solute, factorial. And if we do that, that's 6 factorial. Now, that's the total number of arrangements. But if I were to swap this O and this O, would this be distinguishable? Or this O and this O, would that be distinguishable? Or how about that one and that one? None of these swaps that I'm making over here are distinguishable. So really, for each of the 4 solvent particles, there are 4 factorial degeneracies caused by those indistinguishable changes. And similarly, if I were to try to swap these guys over here, you would see that there's no change. And so there's 2 factorial degeneracies for that. And so we get 6 factorial over 4 factorial, 2 factorial. Here's a nice little trick for evaluating these. Factorial is 6 times 5 times 4 times 3 times 2 times 1. But look what happens if we were to stop at 4 factorial. Divide this by 2 factorial is just 2 times 1 times 4 factorial. These cancel out, and we get 30 over 2, which is 15 unique arrangements, or completely distinguishable arrangements, for arranging 2 solid particles and 4 solvent particles. For energy, things get a little bit more difficult. So in energy, we are arranging quanta, which are units of energy, amongst molecules. And the difference here is, unlike a lattice, where each cell in the lattice can hold only one particle, one molecule or one particle can have as many quanta as it wants. It could have 1 quantum, 2 quanta, 3 quanta. It could have 0 quanta. So how would we write this? Well, what I would do is, let's start with my 3 quanta. I'll just use Q. And I'll use a nice red vertical line for separating them. So here, this might be molecule number 1. This one's number 2. And this one's number 3. That's one possible arrangement. What's another arrangement? Well, another possible arrangement is 2 quanta on molecule 1. None on molecule 2, and 1 quantum on particle 3. That's another perfectly valid arrangement for these quanta. Why don't you guys pause for a second and come up with all the possible arrangements of these quanta on molecules. By now, hopefully you found that there are a lot, but they're not the same as counting lattice. I'd like to show you a trick for counting quanta. If I take each of these partitions between molecules and I turn them from a line into a P for partition, we find something very interesting. Trying to arrange 3 quanta on 3 molecules, and 3 molecules just means having 2 partitions between molecules, really comes down to arranging 2 different types of objects, 3 of object Q and 2 of object P. So if I were to try to arrange these, ways of Q and P would be Q plus P factorial over Q factorial, P factorial, like we saw in the previous one. Now P here refers to the number of partitions, which the number of partitions is the number of molecules minus 1. So I could rewrite this as the ways of computing energies for Q and M molecules as Q plus number of molecules minus 1 quantity factorial over Q factorial M minus 1 factorial. And if we try this on our example over here, I get 3 plus 2 factorial over 3 factorial 2 factorial, which is 5 factorial over 3 factorial 2 factorial, which is 5 times 4 times 3 factorial over 2 times 3 factorial, which is 10. So hopefully you found the 10 arrangements of 3 quanta on 2 particles. And hopefully you'll be able to apply this to all of your problems moving forward. So just to review, if we're counting particles in a lattice, or just particles at all, the ways of counting particles is j objects plus k objects factorial over the degeneracies for j times the degeneracies for k. If we're counting energy, then it's q quanta plus p partitions factorial over the degeneracies for the quanta, the degeneracies for the partitions, and here the number of partitions is just the number of molecules, -1. Try doing a couple of more of these calculations and you'll get some expertise at them, and they'll be hopefully much more simple.